Good morning. Welcome back from the break. Welcome to the session Physical Emissions. We have three papers in this session. First paper will be presented by Dev Mehta from WPI. The paper is called Bake It Till You Make It, Heat-Induced Power Leakage from Masked Neural Networks. The paper was written by Dev Mehta, his colleagues Mohammad Hashimi, David Kobla, Dominic Fortif, and Fatame Ganji. Dev is a PhD student at WPI. His advisor is Fatame Ganji, and before he was at TU Berlin for his master's. Dev, the floor is yours.
So, hello everyone. My name is Dev Mehta, and I'm excited to present our work, Bake It Till You Make It. So, first we'll talk about the problem. So, deep learning accelerators have been an integral part of edge devices. And now with smartphones and new announcement by all the major companies about AI being the focus, they are more important now. And their protection is also as important to us, especially the weights and architectures. They put a lot of sweats and efforts, like years of work, to train the models and then give it to us in a small form factor in a chip. And we want them to work. So now the malicious people who want to steal those IPs to make their own inference engine would like to take the weights and architecture. So side channel resiliency, that's a good answer to it, right? And one of the way of doing it is masking. And masked neural networks have been studied recently. There is an example of MaskNet and BOMANet. And most recent and most efficient one that is there is ModularNet, which will be the focus where we attack. But are the masked implementations actually safe? And that's the question that we answer today. Not really. There have been lots of vulnerabilities shown for those. One of them is temperature. And as you can see here, there has been an experiment done by Noodle and authors about linear functions of masking. And with two shares, they have been put the chip device under the thermal chamber and showed that with higher temperature, leakage is faster and more pronounced. As you can see here, for 50 degrees Celsius, it leaks much faster than normal temperature or the 70 degrees Celsius. And now the question is, can you do this for a larger circuit, like a neural network or any other masked circuit? Can you do it without an external temperature chamber or expensive equipments? And lastly, can you do it without changing the design or using a specific RO or other circuitry, changing the bit stream itself? And we say yes, and we'll show you how to do it today. But first, I'll just go to the basics of the masking. Masking is a sharing scheme for secret variables. There are mainly two types of masking, Boolean and arithmetic. And the idea of the masking is the shares that are created for the secrets have to be kept independent anyhow possible. And one of the way of doing it is domain-oriented masking, where you have two different domains, domain 1 and domain 2, working on different shares. And whenever they cross domain, especially in nonlinear functions, you want a refresh bit, which is normally generated by a random number generator. And that's how you protect a masked design. And we'll see how it is used for the modular net case, where we have, we have two masked circuits mainly, the activation function and the output function. But first, we have inputs which are stored in a VRAM, which is an input VRAM. I'll explain how this is important later. The shares are created and then multiplied and accumulated. Here, these are arithmetic shares. They are 15 bits, and they are given to the activation function, which will output a 1-bit Boolean share, which is stored into a layer VRAM. So this is done for each and every input neuron in the input layer, one by one. And the layer VRAM is populated by the outputs of input layer. Then for the next hidden layer, you start from layer VRAM, get it to the weight multiply and B2A converter. So here weight is multiplied, and for the accumulation, you need 15 bits or an arithmetic share, and the output of the activation function was a Boolean share. So this B2A converter is very important here. And then the same process is repeated for all hidden layers. And for the output layer, instead of masked activation function, you choose a masked output layer function. and it will give us the output of the neural network. So as explained here, all of this is done neuron by neuron, and the mask modules are activation function and output layer. Now, how does the security of this stay? Because it's a masked neural network and we are worried about the security. So we tested using TVLA, where the boundary is plus and minus 4.5, and it shows 99.999% confidence that this circuit leaks, but it should not, right? So what is happening here? It's supposed to be designed masked. So to test that, we use a tool called Verica. Verica is a verification tool used for pre-silicon, where a circuit can be tested to see if fails or passes the security notion. They have capabilities to do side channel, fault, and combined attacks testing. And for our purpose, we use the glitch robust probing model as we are doing side channel. And they also have a composability properties of SNI and PNI. How does it work? You give it the module netlist with annotations where you specify what are your secrets and what are your control signals, and it will tell you if it passes a particular security model or not. Now, we use this tool on the circuit that we have. We check all of the modules individually, and we found out that the binary to arithmetic converter, which converts the Boolean shares into arithmetic shares but for the hidden layer, is the one culprit. And the reason is the concatenation module used here, which concatenates random bits to the Boolean shares, is showing glitch. And to stop it from happening, we move the concatenation module to before the layer BRAM, as shown by the orange lines. And now this, when tested again with the TVLA, shows no leakage at all. So for 2 million traces that also. And then this is the circuit that we use for our attack approach. And now I'll move on to our attack approach. So as told before, we want to use leverage temperature. And here we do heat-induced power side channel. So the side channel is still power, but it has been made better by using temperature. And we use the component BRAM, which I talked about before. And it's a native component. So we are not adding a new component. It is an integral part of the design. And what we do is we flip the inputs. So every clock cycle, you supply alternate patterns of inputs, so 0 to 1 and 1 to 0. For our data set, it could be, it was images, and this is an example image kind of a thing where you have a chessboard kinds pattern where it's flipping every clock cycle. And this will heat up the FPGA internally. And this in turn increases the order of the attack. But the question is, why are BRAMs used if they are there? So for an accelerator, we want good efficiency. And for that, throughput and latency are important. To see what happens for the throughput. So if you are having weights or inputs streamed every time you need them, then you would have to do much more memory calls. There'll be like lots of IO overhead, and that would reduce our throughput and latency. So on-chip storage is very important, where the weights are always available. And this goes the same for the input circuits. So whenever there is an input, the BRAMs will be used to store them, and it will give a faster access. And this is very useful in a case of neural network, where, as I talked before, for the input layer, each input neuron has to be calculated, and they all have the same inputs. And every time getting an input from off chip is time consuming and introduces lots of latencies. And to have a good memory storage, BRAMs are like cache of FPGA. You store it on the device and it's faster. So that's why BRAM are the most efficient use of this. So how do we use BRAM to generate heat? By flipping. And these are the results for heating. So as you can see, when the flipping inputs are given to the BRAM, you can see as high as 30 degrees Celsius increment, and it reaches 70 degrees Celsius for the temperature. And then we studied what would be the effect of heat on gates and what is the physical element that changes. And so there has been studies on this a lot, especially for reliable circuits and chip development. And as you can see here, the increase in temperature will change the threshold voltage at transistor level, and that would change timing of the gates. And we tried and experimented with this on our own. We saw how it works. And we experimented with a single FF and a chain of 10 LUTs. And as you can see here, the timing changes significantly. So there is a decrease in delay in both the cases. And we believe this is the reason for the glitches happening, because the shares are not parallel anymore. They are not computed with the same timing. Some gates will have different timings, and this temperature will enhance the inherent process manufacturing defects that are there in each and every transistor by inducing even more delays or less delays, depending on how the temperature is. Before going on to the results of we will go through experiment setup to see what experiments. Okay, yeah. So we used Chip Whisper Husky for our oscilloscope, and Arctic 7 FPGA on Chip Whisper 305. For power supply, we decided to use a low noise power supply so that we have cleaner traces and less post-processing is required. And the design frequency has been kept as 10 megahertz, and the sampling frequency is similar because we are using the synchronous sampling feature of the Chip Whisperer library, where clock jitter and other noises are reduced due to sampling being synchronous with the oscilloscope and the design frequency. And now I'll talk about the results. In the results, for all of the results, the main two parameters are that the heat generator is on or off. Basically, the circuit is under attack or not. And to have based results, we'll also switch on and off the PRNG, which says if the masking of the circuit is there or not. And for TVLA, as you can see here, the mask circuit with heat generator off and PRNG on shows no leakage for 2 million, whereas the circuit under attack will show leakage. That is, that crosses the boundary. And the next idea is that this leakage seems very little, but can you exploit it? Can you do DPA on it, or can you do some other attack to recover the weights? And for that, we are going to use differential power analysis. And we select two locations on the circuit. One is the second hidden layer, that's around about there. And the other one is output layer at the end of the traces. And we do both first and second order DPA to be more sure of our attack and see how it works. And lastly, the distinguisher we have used is Pearson correlation coefficient, where so here we will take intermediate values for both the layers and correlate them with the power traces in different cases to see any of them cross the boundaries for it or not. So first, we talk about the second hidden layer. So as a base case, we look at the unmasked design where everything is off heat generator and the PRNG, and it should leak, and it leaks. So great. Then for the mask circuit, no correlation is shown here. No weights can be extracted. And on the top, the graph is for how the DPA evolves over number of traces. And as you can see, even with higher traces at that particular location, there is no breakage. No, you can't take out weights from this. And we also tried second order to see if the circuit is working perfectly fine and the DPA is also. So with the second order on the same mask circuit, you can see as good as unmasked leakage, which shows that it's a perfectly working design and the attack. And lastly, the attack. When you turn on the heat generator, it takes more efforts for this location, but you can still see leakage later, and it's exactly at the hidden layer. So this shows that heating indeed affects a large network, like neural network or any other large mask circuit. Especially in this case, we have a non-linear masking also involved, not just linear. Next, I'll show similar results for output layer. So unmasked, good leakage; masked, great, working; second order leakage. And with our attack also, it leaks. Here, it leaks with lesser number of traces, and it's good, better than hidden layer. So the output layer leaks faster. And by this, both the results, we have been able to show that both the masking blocks in the circuit, the mask activation layer and the mask output layers, are affected by the temperature, not just one of them. And to see it better, how effective the attack is, we did 14 wrong weight guesses versus 1 right. And in the black line is the right weight guess, both the cases, hidden layer and the output layer. And as you can see, only those show any possible attack. The others are perfect, and even under heat generator, they would not show any attack. For more details, you can look at our paper where we validate our attack with an external heat generator to show that it was not some power glitch that was caused by our heat generator, which was internal. It was actually temperature that was causing this effect. And those results are there in the paper. Now I'd like to talk about countermeasures and other future works and other ideas that came from this paper. For countermeasures, one of the thing that someone can employ is a power efficient design. So as we know, less power terms of less heat, less temperature. So if the design is power efficient, an attacker has less chances of doing internal temperature increase. They still, if someone has physical access, they can always do external heat generators on them. Next would be what if we just don't use BRAM? And I talked about it briefly before that the throughput and latencies are a challenge when you are using an off-chip memory for an accelerator. But at the same time, when you're talking about off-chip memory, you will have security issues when communicating the memory to the device. And if weights or any sensitive variables are stored off-chip, it's another designer choice and a trade-off that you need to talk about. Other possible heat generators have been explored in research, and we used one which was applicable to our design. We did not want to change the design, so we used the one which was inherently for us. But other designs which are heavily using SRL pipelines or flip-flops or DSPs or other elements could be looked at, and we can see if similar attack could be mounted on different kind of designs. We looked at FF for like storage solution instead of BRAMs, and we can see higher leakage. So this is what we plan to look into in future, like if the same attack could be mounted using a flip-flop instead of a BRAM. And also another thing is the B2A converter, which leaked. It has been also shown by Giggle in 2022 that it has inherent issues. And I'd like to say, like, any designer who wants to use those converters should be very careful, because just having one converter can reduce the whole masking of the whole design, and it's really need to be very careful about it. Lastly, because of the heat generator design, they are internal and they don't use anything specific. Remote attacks are a good possibility, especially once you start using remote power sensors combined with the internal heat generators we have. And this also has a last issue is like noise. So temperature or any environmental conditions when changed inherently have a lot of noise involved. And you would like to use some kind of filters and mathematical or physical to post-process the images, post-process the traces. For us, we used physical filters in our BNC cable to reduce the effect of the noise. And lastly, I'd like to conclude by saying that we were able to demonstrate methodology for first-order attack using a novel heat generator, which just uses internal components, nothing external. And formally tested all of the modules for the neural network using Verica and showed the vulnerability of the B2A converter, and resolved the issue with B2A in modular net, and showed that any large circuit, especially mass neural networks, could be affected by heat generation, which is very simple, but it's very effective. Thank you so much.
Thank you very much. We have some time for questions.
Neat stuff. Were you assuming any knowledge of the neural net architecture? And what kind of architecture were you using?
So we were not really assuming any knowledge of neural network architecture. This architecture was proposed in CHES by Dubé in 2022, and they have the design available. Design not available. It was just the paper, and we looked at that and we replicated the design on our own, and then we worked on that. So we had the design which is there, but nothing else known.
Okay.
Thank you.
Other questions? So let me ask you, do your findings have implications for, if you think about certification of circuits and countermeasures that have to be certified, would you say, yeah, you have to guarantee certain temperature ranges?
I would think so, to have good protections and like other environmental conditions also, like even radiation. Like we know that for space applications, we have NASA understanding the radiological effects and radiation effects. So why not have similar environmental conditions taken into account for look like on Earth devices, I guess. So that would be a good thing if done properly.
Thank you. Questions? And then let me also ask you about the applicability of your findings outside of the domain of FPGA. Can you speculate? Let's say you're in an ASIC environment. What would you pay attention of if you design these circuits?
So because the heating is going to affect the transistors itself, even in FPGA, like at gate level, I would speculate that this would be also applicable to ASICs. And I think there needs to be more research done on like gate level, exactly if routing is affected and if like how difficult it is to maintain countermeasures at like so minute level for different environmental challenges. But I think it's a possibility to affect other kinds of circuits.
Right. Right. I mean, we have seen many of these countermeasures that insert a lot of registers to control the timing.
Yep.
So we would maybe need even more registers or better temperature control.
So yeah, like the ideal case is having register out for every gate, but then you lose all the efficiency that you're looking for a neural network accelerator or any circuit in general. You won't have any combinatorial logic at all. Everything will be sequential. That would be the ideal case. Have flip-flop every gate.
Yeah. Great. If there are no more questions, let's thank the speaker. Now, Dev is not getting off the hook because he's also doing the next presentation. So the next presentation is called 10 Shades of UC Photonic Side Channel Analysis of Universal Circuits. The authors are Dev Mehta, Mohamed Hashemi, Dominic Forte, Shaheen Tajik, and Fatime Ganji. And Dev is still a PhD student at WPI, still not graduated from his advisor, Dr. Ganji. And take it away, Dev.
Thank you. So everyone, again, I'm here. And now I'll present 10 Shades of UC. It's a little different, but it uses one core key component similar, and I'll talk about that later. But let's look at the idea here. Universal circuits have been theoretically proposed since 1976, but like the practical implementation of those was shown after 40 years in 2016. They are basically concepts which are similar to logic locking or obfuscation, where a circuit is kind of hidden by making a circuit universal circuit. And the idea is that you have bits which help you do that. And that's why they are supposed to be applied to IP protection, and it helps IPs being there. The main two features for the universal circuits that make them very easy to implement nowadays is the modular design proposed by the compiler, and that any circuit can be turned into a universal circuit, which I already talked about. And we showed how to break them. They're mathematically almost impossible to break, or rather impossible to break. And with side channel, everything is possible. So I'll first go on to the magical modular blocks that we talked about. There are three kinds of blocks, X, Y, and U. The X and Y blocks are used for routing, and U block basically acts as a 2-input gate. I'll explain how it works, but basically, as you can see, there are terms called CB, which are called configuration bits. And for X and Y, it's 1-bit configuration bit, which will decide either it's parallel or cross. And for Y, it's more like a selector, select any of the inputs of A and B. And for U block, it's opposite. It's about A and B being acting as a selector for the configuration bits, which are the secret. And as you can see here, there are 4 configuration bits, and they basically act as the truth table of the 2-input gate. And this is basically kind of an LUT design that's implemented here. And it's very similar to an LUT design. I'll go into depth of how we use this knowledge later, but first I'll just talk about the UC compiler and the attack approach. So as you can see here, there is a 1 XOR gate, or as I like to call it, 1-bit summation. And we have it passed through universal circuit compiler. The compiler accepts an SHDL format, and it gives us this block and configuration bits. And then we have our own way of converting it into Verilog. But for us here, the important part is the U2, or the blue block, which, as you can see, has a configuration bit of 6, which is basically the truth table of XOR. And the X and Y blocks around it are using basically routing it in a way that this circuit acts as a universal circuit to someone who just views it externally and does not know what are the configuration bits here. And what we do is we do photon emission, and we have 2 attack phases for it. First is profiling, where we build data sets of photon emission of all the blocks individually. So X, Y, and U. So we have 3 data sets for those. And in the attack stage, we capture the victim circuit and use data sets and compare and get the configuration bits. Very simple on paper, but hard to do. The reason why this works is that each and every block with a specific configuration bit will have a specific photon emission fingerprint. And this fingerprint can be utilized again and again to break victim circuits. And the last question is, how do you get this photon emission thing working? And the reason is flipping inputs. Again, I like flipping inputs, I guess. So you flip the inputs every clock cycle, and the transistors have lots of activity because you're making them go from 0, 1, 1 to 0 every clock cycle, and they generate photons instead of sweat. This works out great for me. These photons are easily readable through the backside, and we'll see how the setup looks. But first, I'll go into depth of how this photon emission works for the 3 blocks. So we use 6 input patterns, where we have 3 inputs. F denotes flipping input, and 0 and 1, the standard digital inputs, for both the pins A and B. And the last one, the F, has a bar. It's a little not visible, but there's a bar there. So one is F and another is F bar. So non-synchronous kind of thing. But basically for X and Y, for Y, I'll explain. It's very simple, and X is similar. So if I give the A pin there for configuration bit 0, flipping input. So A port, input port, will show some emission. And if the configuration bit is 0 and that flipping output is seen, so C also flips, we see the emission at the output pin also. And that's as simple as that, you know, the configuration bit. So for LUTs or for a circuit, this is how the logic works for Y. Similar logic can be applied to X. But for U, it's a little complicated. Because even if I give directly flipping input to A, it will just flip C0 and C1 alternatively every cycle. It won't directly show emission at the output. So to explain that, I'll use this example. Here, flipping of first 2 blocks in the layer will give us flipping bits of C0 and C1 for the top Y block, and the bottom Y block will have C2 and C3 flipping. And because the B is constant 0, at the output, you will always have C0 and C1 alternating. Now, based on the values of configuration bits. So if C0 and C1 are alternating, you will have some emission at the top Y block and the output. But if they are same, you won't have emission. So if both of them are 1 or both of them are 0, even though they're alternating between each other, you don't have emission. And we use this trick to see the emissions in U block. And that's why you need 6 patterns. Even for X and Y, you don't need all of the 6 patterns. But for U block, you need all the 6 patterns to get the maximum possible information side channel from the blocks. As you can see, all the 6 pattern will have different configuration bits alternating every clock cycle. So now I'll go to the experiment setup. We have an FPGA which is to do all this work on. We program an FPGA with a universal circuit computer to control inputs using Arduino and get the images and process them. The FPGA is a Xilinx 2 board with Kintex 7 28 nanometer FPGA with fan and heatsink removed so that the flip chip package is exposed and you can do photonic emission from the backside. And the microscope that we use is the AlphaNow microscope. I'm sure AlphaNow people outside and you have all seen them. So those are the people who gave us this nice thing and we can use it to do photon emissions. Lastly, something like this is achieved and we can basically do experiments now, right? The results are simple as seen from before, right? Nope, not actually. It's unfortunate that there's lots of noise in real environment and you need to go through it. Here we can see speck of lights for humans. We can see something, but this is not usable at all. And for a computer, if I give it to a computer to process, it's a nightmare. So first we have an image processing pipeline, which helps us make it better. The raw images are taken and then we crop the block of interest. It could be U, Y, or X, depending on the need. After cropping, we remove the noise using multi-layer filtering, median and bilateral filters. And after filtering, as you can see, it becomes a little bit dull, and that is still difficult for an image processing algorithm. So we do a little bit of contrast enhancement and increase the dynamic range of the images. And that could be given to a feature extraction module. Here we use SIFT for it. But what are this speck of lights? Let's just look at it inherently. So we used FPGAs for our implementations. So we have LUTs here. And on the top with the reddish hue is the Y gate. And as I talked before about the inputs and the outputs being visible easily when you flip, as you can see, it forms a slight Y kind of a shape because I'm flipping both the inputs and one of the input is being transferred to the output. Similar thing for X. And for the U block, as we have 3 Y blocks, you can see all 3 of them individually lighting up. And there are buffers to show where the outputs or the inputs are lighting up or not. And you can see similar placement in the Xilinx Vivado floor plan. And this is very helpful. Okay, now I can show you how that actually works, like how to get the configuration bits of this. So as I talked about, 2 phases. First phase is profiling, where we take images for every block individually for configuration bit and input patterns, all combinations. You take them, you store them, and you store basically the features of those. And it's called a bag of features. So you have 3 bag of features, and that becomes your data set that you're using for attack. In the attacking phase, you have a large victim circuit like this, from which you take out 1 block, you pass it to the image processing and extract features from the query image. And then you can do image retrieval by similarity. In this, it basically checks how similar 2 features are for both the images from the data set and the query image. And it spews out top 5 images from the data set which are similar to this with particular labels. And for this example, these are the top 5 images. Now, our label for the query image was 68. And that's, according to the algorithm, it's the similarity score for 84, and it's the second image. So for this particular input pattern image for the victim circuit, and for this particular block, we say it's a rank 2. And I'll explain how rank comes into pictures by using an example. And our example, summation circuits are back. So this is how it looks when implemented on an FPGA, with all the 6 blocks implemented here. And then each and every LUT is checked and each and every block is taken into account for individual configuration bit extraction. So, okay, matrix, yes. So success rate. So the ranks that we talked about are used to find success rate for the whole circuit in general. And for each block here, as you can see, there is a particular rank associated, and that has been found in the process that I showed before. And based on the ranks, you can say a success rate for that image or that input pattern. And for here, for example, you get 2 blocks, X0 and Y3, which with rank 1. And that's why the success rate for one image is 0.33. But you can take it to all 6 input patterns into account. You have the images for those. So when you do that, it improves. It goes to 0.66. And then you can increase the order. So you can take into account rank 2 also, rank 1 and rank 2 both together, because they have high similarity scores. And you can say with success rate of 1, basically 100% efficiency, that you can extract all the configuration bits from the image. And this is how it works. But let's look at a bigger example. When you use a C17 benchmark from ISCAS 85, it has 6 NAND gates with 5 inputs. And when you put this through the compiler gives out an 81 block image. It's too large to show here also. And manually, a horrible task as a PhD student to complete takes a lot of time. So to make it better, we actually employed a divide and conquer approach. We used the 2 input gates, 2 input signals, and took it to the first U block because we want to see how the gate configuration bits could be extracted easily. And we have 17 blocks here. And here the success rate is much better. Sorry. Go back. Okay. So as you can see here, we did it 3 times to see how good our accuracy is on a good circuit, like a proper circuit, large circuit. And as you can see, out of all 3 times, when you take all 6 of the images into account, 2 times we get 100%, and 1 time we missed 1 block, so 0.91%. But this shows that our attack works on larger circuits, and you can go for bigger circuits or as big a circuit as you want. And I'll show what are the little bit of difficulties or countermeasures for this. So as I told, when circuit becomes big, it's nightmare for someone to do it manually. And automation would be a very good idea for those big circuits. Also, that would increase the efficiency and make this a real world attack. As also talking for the larger circuits, if a circuit is too large, it might not fit in under your microscope properly. Like the microscope can only focus in one particular region of the FPGA, and you might want to move around. So the number of images increases per input pattern. So right now for all the experiments, we use 1 image per input pattern. But if the microscope moves around, it will be more than 1. And that's why the setup is also important. When talking about setup, we can talk about resolution and measurement time. So a better lens will have better resolution, better imaging, and you can see more elements of LUT more clearly. And this would improve the post-processing, and you can even do better attacks, just more than simple image fingerprinting, and also better cooling of microscope. So the noise that you see is mostly black body radiation. The microscope that we used was already cooled till minus 25 degrees Celsius and still generating so much noise. So if you have a better cooling, so there are other microscopes with minus 70 degrees Celsius cooling, and they have much better resolution and much less noise. Next is, I want to talk about another vulnerability. So another UC compiler, an efficient version for an FPGA was shown recently, and we were able to do the same attack on those circuits. And this same thing could be applied to ASICs. We have not tried it because we don't have ASICs for this. But we believe that because the ASICs use standard cells and repetition again, so you can just profile the standard cells and use the same attack for an ASIC. Also, the computer vision techniques we used were off-the-shelf components, but there are more advanced computer vision and AI-based techniques which are being developed for failure analysis every year, and those could be used to make this attack even better. Lastly, I would like to talk about some countermeasures. One of the countermeasures is real-time refreshment of block placement. Obviously, this is not applicable to ASICs because you don't want to move blocks in ASIC real time, but for FPGAs, this could be used. And basically, if you don't have a particular circuit at a particular location for a long time, how do you think of taking images for that, which requires some amount of time? And next is package level countermeasures already, which exist and there are more and more developed. Any intrusion detection could stop the circuit from working. You can stop people from changing input if there is an intrusion. Those kind of things could be done. So to conclude, we were able to break UCs. We are the first team to show it using a side channel. Successfully used to reverse engineer the circuit, photon emission. Off-the-shelf techniques for computer visions were used. And I like to stress that this is not a specific attack for a specific compiler, but anything which could be fingerprinted or could be replicated, we can attack those circuits. Thank you so much.
Thank you. We have again time for questions.
Hi, thanks for the talk. Very nice presentation. I have two questions. The first one is, if you go back to your slide number 7, you have some of the emission images. If you can, if you cannot, maybe we remember.
It's going to take a long time. Yes.
Yeah.
Okay.
One back. Okay, so the question is basically, so how exactly were these images acquired? Are these like single shots? What's the exposure time? That kind of information. Like are these single photons, or is this like a single trigger event, or like are you continuously triggering and this is an image of 2 seconds accumulation, or?
Yeah, so it's an different accumulation times for the testing, but what we used is around 3 seconds. And it's because the inputs are continuously given. And because the circuit is more or like a combinatorial circuit, you don't have any issues from giving continuous images. And it's like a higher accumulation of lots of photons from a particular location, more or less.
Okay. So I can see that you can do that in the, let's say, the profiling stage, right? Where you figure out what are my features and so on.
Mm-hmm.
Do you need to do the same in the attack phase?
Yes. So once the victim circuit is kept in, you need to do like supply inputs to the victim again, and they would have the similar photonic emission over time.
Okay, but so in a scenario where you don't have that level of control, that wouldn't work that way.
So for this kind of adversary model, you have the circuit and you can give it any input you want for as long as you want. So you would always have a control once you have the physical device, because this is like a physical attack.
Okay, thanks.
Thank you.
I got a question. So basically your attack will work. You're almost replicating the attack on the meta structure, correct? The UC is just a meta structure similar to the FPGA structure that is just programmed the same as the FPGA fabric will be. So this is an attack that will work with all kind of that configurable fabric scenarios. Is that right, or I'm wrong?
So here, each and every block is designed particularly for the LUT, and for that LUT, you can fingerprint the whole LUT emission in that particular scenario, and it would work for all kinds of LUTs. You just need to profile those kinds of LUTs again and again, and for standard cells also it should work basically. So it's modular design being used by us to do attacks better, I would say like that.
So let me rephrase it a little bit. I can use the same attack to reverse engineer a lookup table on the FPGA.
I guess so. Yeah, I believe so.
So it's not content dependent. It's infrastructure. You're attacking the programmability of the UC circuit in some form.
Yes.
Thank you.
Thank you.
More questions? Let me ask you a question about the flip chip model. So your images show the transistors, right?
It shows the emission, yes, from the
The
transistors.
emissions
Yeah.
of the transistors. So you need to have a direct line of sight to a transistor, which is what I assume is the case in your flip chip mounted FPGA.
Yeah, so there is a silicon layer, but the emission that the transistor is giving is like near infrared, which is transparent to silicon. So silicon acts as a transparent layer between the transistors and the photon emission, photon microscope.
So what if I have a traditional circuit, for example, that sits in wire bond package, or maybe like on the other side, the more advanced packages, multi-chip modules, where direct line of sight of the transistors might be a challenge. What would you do in that case?
So then you have to like pre-process the whole package at hardware level. So some people try to like desolder the package, flip it, and then sand on the other side, like polish. So you need to do all those techniques to get access to the backside first, and then you can do the attack again. But that requires more efforts on the attacker side to get the chip ready to be put under a microscope. When it's a flip chip packet, you can directly put it under a microscope.
Right. These would all be steps that standard failure analysis
Yes.
people have to do as well. Yeah. Thank you. Great. No more questions? Oh, question here. Go ahead. Yeah, the mic.
Somewhat a related question to the first question. What was the switching frequency of the inputs of the circuits?
It was just the standard switching frequency for the oscillator, which was 200 megahertz.
Excuse me, how high?
200 megahertz.
200 megahertz, okay. And have you seen, this is a 28 nanometer device, right?
Yes.
Have you seen, or what's like the increase you see when going to smaller technology nodes? Have you tried out anything?
I have not tried out smaller technology nodes, but if you go to smaller technology nodes, you need a better lens. This lens was good enough for 28 nanometers, but you will have more noise and like the LUTs will become closer and smaller. So it's harder to see those features carefully. That's why I talked about like higher resolution lenses being more effective for smaller technology nodes.
Yeah, of course. Okay, thank you.
Great. All right. Thank you, Dev. Our next speaker is Lars Renks. It's being controlled. Go ahead. So his paper is Through the Looking Glass, Sensitive Data Extraction by Optical Probing of Scan Chains. The authors of the paper are Tuba Kian, Lars Renks, Marvin Sass, Antonio Saavedra, Norbert Herford, Eltham Amini, and Jean-Pierre Seifert. And they're all at TU Berlin. And Lars is a PhD student at TU Berlin.
Yeah, thank you very much for the introduction. One correction, Norbert Herford is at IHP Leibniz Institute, but doesn't matter. Okay, thank you all for being here. Title of my talk, Through the Looking Glass, Sensitive Data Extraction by Optical Probing of Scan Chains. So I'm going to start out with some background on scan chains, why they're used. Then I'm going to explain the threat model and our attack approach. I'm going to describe like the verification of our attack approach that we did. And the last step, I'm going to show how to break scan chain obfuscation. I cut the countermeasures of this presentation, but I left it in this overview. Yeah, maybe in the questions afterwards. So yeah, let's start with the design for test. So design for test is used in post-manufactured devices, and it's basically there to increase the test coverage of your device. Yeah, it is used to detect manufacturing defects, and is also used to perform functional testing of the device. And the idea is to increase the controllability and observability of the device. And yeah, it is done by inserting additional logic to your netlist. Yeah, And one of the main things in DFT, or one of the main introductions to your circuit, is the so-called scan chain. So you can see the scan chain highlighted in red. And the basic idea is, in front of all your flip-flops, or all the flip-flops you want to become scan flip-flops, you introduce a multiplexer that is controlled with the scan enable. And this makes it possible, if you assert the scan enable to high, you basically have all your flip-flops connected in a big shift register. And yeah, so the normal test flow would be you assert the scan enable, you shift in a test pattern, then you deassert the scan enable, and you run the combinational logic for one or more clock cycles. And then you assert the scan enable again, and you can shift out the response of your circuit. And yeah, a structure like this drastically decreases the testing time in post-silicon testing stage, and it's a critical, it's critical to save cost in testing to introduce such scan chains, and they're basically used in all devices nowadays. So scan chains have been able to, or it has been shown that scan chains are a pretty big side channel, and they can be used for side channel attacks. So an attacker could use them to change or disrupt the operational stage, and they've also been shown to be able to be very beneficial in reverse engineering the device. So you can imagine, if you can put the device in any stage you want, have it operate for a clock cycle, and then shift out the response, you can directly reverse engineer the internal logic. So to prevent attackers from doing so, there have been several countermeasures. So one of the most obvious one is disabling or restricting the scan chain after testing. So you can do that by burning e-fuses, or burning the e-fuses basically. Then there have also been approaches in resetting all the scan flip-flops when you have like a context switch between normal and test mode, but schemes like this also restrict the testability of your device. Then there are, in big devices, schemes like scan compression and dynamic scrambling of scan flip-flops are used. But what we've been concentrating on is scan chain obfuscation or scan chain locking. So in scan chain locking, additional to the multiplexers you introduce in your scan chain, you also introduce these XOR gates. And these XOR gates lie in the data path. And depending on certain key bits, you invert the data or not. And then the secret key kind of obfuscates the scan data. So only, I'll go to the next slide. Okay, so what we're trying to do is, we still want to be able to, you can see like the scan in data A5 to A0, and the scan out data B5 to B0. And these are obfuscated by the XOR gates, and subsequently by the key bits, K0 to K2, K0 to K2. And what we want to be able to do is, basically find the inversions that are happening in our data path to still be able to reverse engineer the combinational logic of the device. So our attacker's approach is first decoding the scan path semantics. Then we need to do like a spatial localization of all scan flip-flops in our design. Then we need to localize our specific target flip-flops on the chip. And the last step is then extract like sensitive data of these flip-flops. We have basically two different experiments. One experiment we run on a USB to SPI chip that was provided by the IHP. This is produced in 250 nanometer CMOS technology and runs on 2.5 volts core voltage, and it hosts scan chain with 2,100 scan flip-flops. And then the second experiment we did on a Intel Cyclone 4 FPGA, which is produced in 60 nanometer technology and runs on 1.2 volts core voltage. Our setup, our optical probing setup, you can see here a block diagram here. So basically, we have an infrared light beam that passes through the backside silicon. As mentioned before, silicon is transparent to infrared light. And then this infrared light beam will interact with the active devices on the front side of the device. And yeah, depending on the voltage that is applied on the silicon, the index of reflection will change, and the reflected light then goes back through a beam slitter and gets detected by a photon detector. And then we basically have two possibilities. So for EOFM, which is short for electro-optical frequency mapping, we run that through a frequency analyzer. And in the end, we get a 2D frequency map of a selected area. But we can also just run the detected light through an oscilloscope, and then we can do EOP, which is short for electro-optical probing. And we just get the waveform of the spot where we parked our laser beam. And then the last measurement technique we used is LLSI. So here we modulate the core voltage at a certain frequency and then perform EOFM. It will get clear later on what's the benefit of LLSI. So like I said, the first step is decoding the scan path semantics. So imagine you want to read out like a specific protected register on your device. And if you want to use the scan chain, you need to know which position inside the scan chain is this specific flip-flop of interest. So the first step is to reset the device on a test to its initial state. And for our case, we want to know we decided to read out the SPI data register. So the chip acts as a USB to SPI bridge, so it was pretty easy to just like program the SPI data register via USB into a known byte. Then we switch the device to test mode and just shift out the scan pattern. And then we do that multiple times. And by observing the shifted out scan pattern, we can then identify, okay, scan flip-flops, let's say 1900 to 1908 are the SPI data flip-flops. Okay, the second step is like the localizing our scan flip-flops by EOFM. So to do that, we have to do two EOFM measurements. So we just run the scan chain with like a known clock frequency, and we run it at a data that we also switch the data at half the clock frequency, which results in shifting alternating ones and zeros into the scan chain. So here you can see on top, if we then perform EOFM at the clock frequency, we see all the spots on the device that are modulating at the clock frequency. And at the bottom, we performed EOFM at the data frequency, and there we can see all the localizations on the device that are modulating at the data frequency. So if we look at the EOFM at clock frequency, we can see the spots that are highlighted in red. These are suspected scan flip-flops, and you can also see the spots that are highlighted in yellow, and these are suspected clock buffers. And we can do this, or we know that because when we look at the data frequency, we see the flip-flops, they should modulate at clock and data frequency, whereas the clock buffers will only modulate at the clock frequency. And then all the other spots, this is the combinational logic. The combinational logic will only modulate at the data frequency and not at the clock frequency. So by doing kind of a subtraction of the two images, we can localize all the scan flip-flops on our device. Okay, then the third step is the localization of our target scan flip-flops by LLSI. So here we also first initialize, so we need to do two experiments in parallel here. We modulate the core voltage at a known frequency. So we will have like, for example, if we are running here at 2.5 volts, we would have the core voltage modulate between 2.4 and 2.6 volts at a known frequency. Yeah, and then what we will do, we will first initialize all scan flip-flops to 0. We stop the clock and then do an EOFM measurement. So this is the first measurement we do, and then the second measurement, we will shift in a logic high to exactly the scan flip-flop we want to localize, stop the clock, and do an EOFM measurement. And what we then do, we subtract the two images again, and where we see a difference, this is where we suspect our target flip-flop to be. So here you can see how that looks like. So first, we filled all the, so at the image A, you can see we filled all the registers with a 0, except the target register, which is filled with a 1 now. And from there, we subtract all registers filled with the logic low. And then you can see the subtracted image. We see like very clearly at which spots the two images differ. And then if we add this to like the location of all the scan flip-flops, we can see, okay, there are like our two registers of interest in F of the superimposed image. So this is actually the SPI clock and the SPI data registers. And then the last step is running EOP. So we just park the laser beam on the specific spots of interest, and we have the device run a normal operation. And there you can see pretty clearly the SPI clock with like the regular clock frequency and the master out slave in register. And we can read out the byte of interest, which is here. Yeah, FD55. Okay, then for the other experiment we did on the FPGA, so there we implemented a locked scan chain, which you can see here in the image. So we have a scan chain of 6 scan flip-flops, which is a pretty academic test case, which is obfuscated by 3 XOR gates. And we assume that the number of the XOR gates and their placement within the scan chain are not known to the adversary. So here again, here you can see EOFM at a clock frequency of 6 megahertz. The data frequency was set to 3 megahertz with a 90-degree phase shift, again resulting in shifting like alternating ones and zeros into the scan chain. And then so this is done again to localize our scan flip-flops on the device. And after that, we run EOP on the specific spots where we just shift in one logic 1 and then the rest is zeros. And here on the right, you can see like the resulting waveforms of the experiments. And you can pretty clearly see the logic 1 propagating through the scan flip-flops. And you can also see between which scan flip-flops you have an inversion. So for example, here between scan flip-flop 2 and scan flip-flop 3, you have an inversion. Between scan flip-flop 4 and scan flip-flop 5. And again, between scan flip-flop 5 and scan flip-flop 4, you will have an inversion. Yeah, so to conclude, our primary focus was to like assess the potential risk, which are entailed by including a scan chain into your device. We demonstrate that like non-invasive probing techniques allow for scan chain exploitation. We show that scan chains are a very beneficial side channel for overcoming localization challenge. So you can imagine like this EOP probing, you can do that basically anywhere on the chip, but the scan chains show to be very helpful to actually localize locations that are of interest to us. Yeah, compared to other techniques that have been shown, the attacker doesn't need any knowledge about like how the scan chain is obfuscated or where the XOR gates are. And yeah, that's it. Thank you very much. And I'm open for questions.
Thank you. You have time for a few questions? Benedict?
Thanks for the presentation. I have a question about that slide where you had like image A minus image B equals C and then C plus exactly. So on the bottom right at the end, the superimposed image,
Yeah.
you kind of said, okay, now we clearly see the location of these two registers. And okay, in that image, I see that two of them are like two areas are highlighted with this green box. But if the green box wouldn't be there, how would I know where to draw the green box?
So you can see you can see there are several spots where we have the two subtracted images where they have differences, right? So in like
C,
the
yeah.
image C,
Yes.
you can see there are spots where the two images differ,
Yes.
but the difference of images needs to lie within like the locations of all scan flip-flops, which you can see in image E. Right?
Okay.
So for example, the combinatorial logic is still connected to the scan flip-flops. And of course, if you have a 1 in your one scan flip-flop, this 1 will also be connected to the combinatorial logic, which will also give you a different image, whether there's a 1 connected to its input or a 0. Right? So this is why we have to superimpose the subtracted image to the locations of all the scan flip-flops. And only where these match their our suspected scan flip-flops can be, right?
Okay, so F is actually, let's say, D and E. So whatever shines up in D and in E.
That's
so it's
right.
not, so it's not like plus, but it's like it has to shine in D and it has to shine in E, and
Yeah.
then okay.
It's
Okay.
a superimpose.
Okay, thanks.
More questions? So I was curious about the also about the attack model, as with the previous speaker. So accessing scan chains is pretty strong. Anybody who does a secure chip will sort of by default probably turn off the scan chain. But even so, if it's like a complex SoC where you have high security, low security components, you would probably have a separate testing approach for the secure part and the non-secure part. So I was wondering, in your for the circuits that you tested, what percentage of logic is being controlled by pure scan chains, and what is controlled by different means, like built-in self-test or portions that don't use a scan chain at all, like hard macros or on-chip memories? And
So for the USB to SPI chip that we tested, the whole design was connected in one scan chain because it was a very small chip, only 2,100 registers. So they were able to just connect them all within one scan chain. Yeah, to like restrict the scan access or like burn the E fuses after testing, it has been shown that you can like bridge them with focus ion beam or whatever. So it is still possible to, I mean, the internal structure of the scan chain will still be there even after it's being disabled. And so there have been some papers on like how to circumvent the restriction of scan chain access.
got it. Yeah. Thank you.
I have one more, I forgot. Sorry. Can you give us an idea of the cost of the setup? Like especially the photon detector, I guess, is, you know, not
so all the experiments we did were performed with the FIMOS 1000, and it's like in the range of 1 million euros.
All right.
So it's a capital equipment you need, but inside the failure analysis community, they're pretty well known and well used. And so one of the big risks is like with outsourced testing companies. And these outsourced testing companies, you can imagine that they have like the capital power to acquire these machines.
Okay, thanks.
Great. Thank you. Last chance for questions. Let's thank Lars.
Thank you.
Thank you. And then we're early for lunch. So this concludes the session. Thank you very much for coming. We'll meet again after lunch. 1:30.